begin.
Don't forget those.
Howdy, I'd like to thank you all for joining us here today. My name is Joey Felici, Project Manager and for Legendary Applications. And joining me here today is Brian Roby, our hardware engineer, Brad Swallow, our testing engineer, and Adam Schaefer, our software engineer. Our project advisor is Dr. Wei Zahn from Texas A&M University, and our project sponsor is Russell Treat, CEO of InterSys, a third-party consultant and project implementator for oil and gas production. Now, did you know that in 1980, 62 million barrels a day of oil were used in world consumption? Today, that number has increased to over 85 million barrels a day of oil. 24% of that is United States use. Now, with that, there's been a strong push recently to be less dependent on foreign oil. Now, where does that leave us? We have green energy as well, but we're never going to shake our need for oil, so we need to increase production in domestic oil. And right now, bean pumping consists of 60% of oil production in the U.S. Now, this right here is a bean pump. You've probably seen it on the side of the road while you're traveling through Texas. Right here, we have the motor. It's connected to a V-belt that goes through the shaft, and it's turning this crank. This crank has a counterweight right there, which is pivoting this bean pump all the way down and grabbing the oil from this rod string right here. And now, if we continue that down into the wellbore at the oil reserve, down to this rod string, you see that it's connected to a plunger unit. This plunger is incorporated into the tubing wall, which the oil will then travel up to. Now, on an ideal system, we'll have our large oil reserve creating a high pressure system. Now, in here we want a low pressure system, so naturally high pressure will flow into a low pressure system. This will be regulated by two valves. This one the traveling valve, this one the standing valve. And as you can see, when this plunger goes down, the traveling valve goes up, allowing for the area above here to fill with oil. Now, whenever the plunger goes up, the traveling valve goes down, the standing valve comes up, and oil is allowed to fill into this area right here. Now, what we have over here on this low pressure system, the reservoir has depleted a little bit, and it's now created this lower pressure area. So we're not getting the production that we should be getting. Now, normally what they do is either through pump on off control or variable speed drive control, they'll either turn it off or slow it down so that they can increase the pressure in that area, either artificially or naturally let it increase. Now, currently our objective is to create a variable speed drive pump control system that we've dubbed JAP2, which will hopefully maximize efficiency and minimize costs. Now, what we also want to incorporate is reducing the damage of pumping systems through previous methods of control. Either this be through systems where gas would form into the tubing, or the grinding of the rod string on the inner tubing, what have you. There's plenty of different methods where it will damage the system. And finally, we want to incorporate SIGCOM and SCADA to increase the overall functionality of our unit. Now, SIGCOM, if you don't know, is a system developed by Crosspoint for InterSys as well. That unit is a control system for compressors for oil and gas industry. And SCADA, if you don't know, is a system to network different units. For our example, pump jacks. We'll throw a SCADA pack out to various pump jacks, and we'll be able to connect to a central host. Now, as you can see from this graph, this is billions barrels per day versus the year. Now, there's a steady increase in blue as to the amount of production that has been increased throughout the year. So, looking from that, we have our general need of oil. Now, right here on our red trend right here, that is the estimated demand at 2% increase per year. And by 2014, it is estimated to be over 100 million barrels of oil per day. So we're going to increase production. Now, in order to do this, we need to decrease or try and reduce any type of downtime in the system, and also try and reduce any type of maintenance costs from the system. So now, as for our problem statement, Legendary Applications is moving forward to expand in 3 key aspects of beam pumping future, either through communications, sensing, and expanded recovery by introducing JAV2. Now, JAV2 will incorporate several features to it. As I mentioned before, the variable speed drive, which will be regulated by old measurement devices that are already in place on beam pumping units right now, such as strain, pressure, voltage, amperage, what have you. And then also by new measurement devices such as an accelerometer, thermocouple, and tachometer. We'll also, as I mentioned before, be incorporating the SIGCOM integration and as a part of Intersys's requirements for this unit. Also, data storage from all the measurement devices and SCADAPAC communication, as well as other terminals of communications such as a local HMI port and a Bluetooth interface for local laptops to come in and download the data that is stored on the system. And we will present this all through a GUI format for easy access. So, kind of an overview of our system. We'll have this centralized area right there with SIGCOM and SCADA, and we will incorporate the VSD to the motor, controlling the motor speed, which will control the pump jack itself. Now, we will get information from existing and new sensors and sensors from the motor itself to try and regulate this variable speed drive, and thus creating a closed loop system in that. And also mentioned before, communications outlets. We'll have the SCADAPAC communicating to the central host via radio wave, a local HMI panel for the technicians to use, and also a Bluetooth interface for technicians' laptops where they can download information such as a dynameter card based on that system. Now I'd like to pass this off to Alex, who will talk to you about the functional diagram.
Thank you. Before I get started with the functional block diagram, I'd like to explain the color coding scheme that we're using. The red blocks represent anything that will be completely programmable and designed. The pink block will represent anything that are partially programmed, and I will explain that in a later time. The dark blue is developed hardware, and the light blue is provided hardware that we will be incorporating into our system. Now, as you can see, this is our interface board. It is powered by a PID microcontroller that is directly connected to a variable speed drive controller, along with signal processing circuits, an RS-485 communication circuit, a power regulator, onboard data storage, onboard indicators, and the previously developed SIGCOM unit. As you can see now, this is how our board interfaces with the beam pump system. The variable speed drive controller sends feedback to the motor, which drives the pump system. Now, our various sensors on the pump system provide direct feedback to our signal conditioning circuits that are processed by our PID microcontroller. We now have our human-machine interface, which consists of an LCD and a tactile interface for local technician usage. And now we move on to the SCADAPAC. The SCADAPAC will be connected to our input board via Modbus communication protocol. As you can see, the SCADAPAC is in one of the pink boxes. This represents that we will be partially programming this unit. When I say partial programming, I mean